So today we're going to start with the normal distribution. What is a normal distribution?
Is this symmetrical?
It's a distribution that's normal. Yeah. So here's what a normal distribution is. A normal distribution is it is an idealized distribution with mean mu and standard deviation sigma. It's an idealized distribution with a mean of mu and a standard deviation of sigma. Now, if I'm using mu and sigma, is it about a sample or about a population?
Population.
It's about a population. Very good, very good, very good. Because I'm using mu and sigma, this is about a population. So it's an idealized distribution with a mean of mu and a standard deviation of sigma about the population. Now, it has two very defining properties. It is symmetric and unimodal. Ladies and gentlemen, the normal distribution is the bell curve. It is symmetric, it is unimodal, and it looks like that guy. It's the bell curve. Oh, I guess that's down here. What does it look like? I just drew it. Here's a bigger version. There it is. Now, let's describe its shape. I kind of already did that. What is the shape?
Symmetric and unimodal.
Symmetric and unimodal. Now, guess what? Because if it has those two properties, symmetric and unimodal, you can actually say that the shape is approximately normal. You can literally use the word normal to define the shape if it has the two properties of symmetric and unimodal. So you can lump those two things together into it's approximately normal. Notice that normal is capitalized. That is because normal distribution is a proper noun. It is a noun describing a specific distribution that is symmetric and unimodal. All right, where is the center of this normal distribution? Because it is symmetric, which measure of center should we probably use? The mean. So we're going to use the mean of mu. And the mean of mu is located right here in the middle. Now, just for funsies, where's the median of this distribution?
Same place.
Also right there. So can I use the median? Sure, you can. We just prefer to talk about mean in a distribution that is symmetric. But you can use a median. Okay? Don't freak out if you see a question that's like, where's the median of this symmetric distribution? It's okay. All right, now for the fun one. Spread. What's the lowest number of this distribution?
Yeah. You said like 0?
So the mean of a normal distribution can be anywhere. So where's the lowest number?
The minimum. Anywhere but probably 0.
So this actually goes on forever. So what's the lowest boundary? Negative infinity. It's an idealized distribution that is possible, can occur anywhere from negative infinity all the way up to positive infinity and beyond. So it's all real numbers. Yes, absolutely. This means, guys, that my normal distribution can be located anywhere on a number line. I can put it anywhere. It could be negative 10,000. It can be positive 4,700. It can be 0. It can be centered anywhere on a number line. So it's an idealized distribution that can go anywhere from negative infinity to positive infinity.
But if it's not centered on 0, wouldn't it technically be like skewed?
No, because I'm taking the whole distribution and I can put it anywhere. So it could have any mean or any standard deviation for any value. You'll see lots of examples where there's an infinite amount of different distributions. Notice I didn't talk about the O. What does O stand for? Outliers. Why didn't I talk about it?
There's no outlier.
Because usually in a normal distribution, we're not going to have an outlier, okay? So most of the time, that's not going to be a thing, okay? All right. Let's look at an example. Chapter 1, multiple choice test scores from Mr., not mine, it's not mine, from Mr. Lakey's 5th period class. So there you go. Follow an approximately normal distribution with a mean of 86 and a standard deviation of 5. We're going to sketch the normal curve that approximates this distribution. We're going to label the mean and the values that are 1, 2, and 3 standard deviations from the mean. You can draw this big. Whee! I promise you guys will get really good at drawing a normal distribution because you're going to draw a lot of them this year. Probably the most drawn thing in statistics. Okay, the mean. What is the mean of this normal distribution? Where on the number line does this normal distribution center? 86. Now, we're going to do 1, 2, and 3 standard deviations. You'll understand why 3 and why not 5 in just a little bit. But for now, 1, 2, 3-ish. That's about where they would be located-ish. How do I know? Well, because I've drawn a lot of these. You guys will get really good at these. But basically, the 3 standard deviations, you're really close to where they are starting to come together. And again, you'll see why it's 3 and not 5 or 10 or 20 in just a few minutes. So, all right, if I have a mean of 86 and a standard deviation of 5, what is the grade for someone who scored 1 standard deviation above average? 91. Does everyone understand where we just got that number?
I do. +5.
We added 1 standard deviation. Perfect. If I go from the mean and I want to see what did someone score that was 2 standard deviations above average? 96. How'd you get that? You added another 5. So in between these standard deviations is 5. There's 5 in between each of these. So what did someone score that is 3 standard deviations above average? 101. Now, is that possible on this test? I don't know. Was there a bonus? Was there not? I have no idea. But it's okay if you go above the maximum or you go below the minimum because this is an idealized distribution. So there are gonna be times where you're gonna be like, oh, but the maximum is this. That's okay. You can continue to do this even if it's above the maximum. All right, so between each of these standard deviations, there's 5. So all I did is I just added 5 each time. All right, let's go the other way. What did someone score who was 1 standard deviation below average? 81. What about 2? 76. And 3?
71.
Do you guys have any questions about how we just labeled that?
Not so far.
All good so far?
I think so.
Okay. All right. Does anyone remember z-scores from last week? What is the formula for a z-score? Value minus mean divided by standard deviation. Okay, let's say somebody scored an 86 in this distribution. So let's say Danny got an 86. What is Danny's z-score? 86 is his value minus the mean of this distribution, which is also 86. So that would be 86 minus 86 is 0. It doesn't really matter what we're dividing by. Danny's z-score would be 0. Okay? He was 0 standard units from the mean. All right? Let's say Maddie got a 91. What is Maddie's z-score? 1. She is 1 standard unit above average. She is 1 value of 5 above average. That's what the z-scores are. If I do the math, 91 minus 86 is
5.
5. And what is 5 divided by 5?
1.
That's her z-score.
That's it.
Okay.
That's so crazy.
All right. Let's say Andrew got a 96.
Hold up.
What is Andrew's z-score?
2.
2. Why is that? He is 2 standard units above average. Watch this. If I take the mean of 86 and I add 2 times the standard deviation, I would get 96. 2 standard units above average is his z-score. What is the z-score for someone who gets 101?
3.
What is the z-score for someone who gets an 81?
-1.
-1. Why is it negative?
This is lower.
It's below average. What is the z-score for someone who got a 76?
-2.
71?
-3.
Do you guys have any questions?
Not yet.
Does that help clarify z-scores a little bit? Okay. Perfect. All right. What about this thing called the empirical rule? It sounds kind of Star Wars-ish, right? Yes. Danny.
So it's the percentage of how much, like the percentage of the data that falls between each standard deviation of the.
I couldn't have said it better myself. The empirical rule is the percent of data that is within each standard deviation. So here's how it looks. I am at the mean right here. If I go 1 standard deviation in each direction, I have captured 68% of the data for a distribution. If I go 2 standard deviations, I have captured 95% of the data. If I go 3 standard deviations, I've captured 99.7% of the data. So here's what it is. 68% of data is within 1 standard deviation of the mean. Now, you guys know what within means, right? It means within 1 below and 1 above. So I go 1 on both directions. So within 1, meaning from the mean out 1 standard deviation. That is where 68% of the data lies. So you guys, remember back when we were doing that, Miss Lakey gets to school at 7 o'clock, give or take 5 minutes, right? And I told you that the 5 minutes was the window, the standard deviation, like of what was considered normal-ish. So 1 standard deviation has a majority in it. That's why we say it's considered the norm, right? 68% of all the observations are going to be just within 1 little old standard deviation. So 68% of the time, Miss Lakey gets to school between 6:55 and 7:05. 1 standard deviation. Okay. So 2 standard deviations. What percent of the data is there? 95% of data is within 2 standard deviations. By the way, this is called the empirical rule. And sometimes you'll see it written as the empirical rule, but a lot of times we just use the numbers. We just say it's the 68, 95, 99.7 rule, which sounds silly, but when you say it with the numbers, then you never forget the percentages. Empirical rule, I might forget the percents. The 68, 95, 99.7 rule, I'll remember the percentages. 99.7% of the data is within, how many?
3.
3. And now you know why I asked you to go 3 standard deviations. Because at that point, you have got almost all of the data. And so why do you need to continue going 4, 5, 6, 7 standard deviations? You're not going to get a lot more every time. Now, when does this apply? Use your context clues. What did we just talk about? A normal distribution. This only applies to normal distributions. So, you have a left-skewed distribution. Can you use this?
No.
Nope. Right skewed?
No.
Bimodal? Uniform? No. None of the things unless it is unimodal and symmetric and it looks bell curvy. Okay? It only works for bell curves. Cool?
Yeah.
Cool. All right. 68, 95, 99.7. 68, 95, 99.7. Okay. Now for the fun part. The distribution of heights of young women age 18 to 24 is approximately normal, with a mean of 64.5 inches and a standard deviation of 2.5 inches. Hey, look, did you guys notice that they use mu and sigma here?
They do.
Why?
Because it's a population.
Because this is about the population of young women. Yes, ma'am.
Pretty smart.
We're going to sketch a normal curve that approximates the distribution of young women's heights. We're going to label the mean and the values that are 1, 2, and 3 standard deviations from the mean. Now, guys, give yourself some room underneath here because we're going to write quite a bit on this. You can make it pretty big, but just make it kind of flat because we're going to write a lot of stuff underneath as well. Also, plot twist, normal distributions can be very flat or they can be really tall like this, okay? They can have different widths like that and still be considered normal. All right, so we've got 1 standard deviation on 1, 2, and then 3. 1, 2, and then 3. And then we're going to label, just like we did with the test scores, we're going to label our values. What is the mean of this distribution? 64.5. All right. If a young woman, age 18 to 24, is 1 standard deviation above average, how tall is she?
She is
67 inches tall. All I did there was I added 1 standard deviation. If a young woman is 2 standard deviations above average, how tall is she?
69.5.
If a young woman, age 18 to 24, is 3 standard deviations above average, how tall is she?
Oh, she said 2.
You guys know why I always go to the right first?
That's easier.
Because addition is easier. Let's go the other way. 64.5 is the mean. If I subtract 1 standard deviation, what is the height of a woman there? 62. What is the height of a woman that is 2 standard deviations below average? 59.5. Subtraction is hard. And what is the height of a young woman that is 3 standard deviations below average? 57. Okay. Now, I'm going to just kind of draw and write on here some things to help you when you're looking at this. Remember where those numbers came from. So this is, I added 1 standard deviation. I literally took mu of 64.5 and I added 1 times the standard deviation. That's mathematically what we did. We just did it different. Then I took 64.5 and I added 2 standard deviations. I know that's not what you actually did.
Yeah, I don't like that part.
You just did 67 plus 2.5, but I want to remind you that if I took the mean and I added 2 times 2.5, I would have got 69.5 as well. Same thing with the plus 3 standard deviation. This would be plus 3 standard deviations. And then if I go the other way, mathematically speaking, this is what we did. We subtracted 1 standard deviation. We subtracted 2 standard deviations. And we subtracted 3 standard deviations. Does this mean that there is never going to be a woman that is taller than 72 inches? Does this mean there will never be a woman that is less than 57 inches?
Only 0.3%.
But that's not going to happen very often. Only 0.3% of the time will we have somebody outside of that 3 standard deviation. All right, we're going to mark some more things. Here we go. What percent of young women age 18 to 24 are between 62 and 67 inches tall? There is 68% of our data is within 1 standard deviation.
How'd you do that, bro?
Because of the 68, 95, 99.7 rule that we just talked about.
Wait, hold on.
What percent of young women age 18 to 24 are between 59.5 and 69.5?
94%.
This is 95% of the data.
95%.
What percent of young women age 18 to 24 are between 57 and 72?
99.7.
99.7%.
I forgot like the within part.
Mm-hmm.
Because you're not paying attention to it.
Okay.
That's true.
What is the Z-score for a woman who is 57 inches tall?
Oh, whoa, yeah, -3. Never mind.
What is the Z-score for a woman who is 59.5 inches tall?
-2.
What is the Z-score for 62 inches? What is the Z-score for a woman who is 64.5 inches tall? What is the Z-score for a woman who is 67 inches tall? And 69.5 and 72. These are the Z-scores. Okay. All right. And now I'm about to find out who should have dropped. Are you ready? Oh boy. Here we go. Ladies and gentlemen, what percent of the data is from 64.5 to 67?
34.
How did you get 34, sir? That was so fast.
Half to 68.
If I know that this is 68 and this is symmetric, how much is in each of these? 34%. So this is 34% and this is 34%. And now I'm going to ramp it up on you. What percent of the data is from 67 to 69.5?
13.5.
Would it not be 34?
He's insanely bad is what I meant. Oh.
Why is it not 34?
Is that what makes sense?
Because the top is curved, you guys.
Makes sense for it to be 30.
And for my calculus people, this would be finding the area under the curve. We could integrate. That sounds awful. Let's just do some simple math. Watch this. What percent is from 59.5 to 69.5? 95. I've already taken care of the middle 68. 95 minus 68 divided by 2 equal sections. What do you get?
13.5.
13.5%.
Thank you.
All right, ladies and gentlemen.
Oh, now we gotta figure out the rest of it.
What percent of young women are from 69.5 and 72? And you can only answer if your name's not Danny or Ryan.
5%. No, wait, 2.5%.
What percent is from 69.5 to 72?
2.5.
It is not 2.5.
2.25.
2.3.
2.35.
3.5.
I'm a genius.
99.7. Take out the 95 here and divide by 2. 2.35% and 2.35%. Ladies and gentlemen, what percent of young women are going to be less than 57 inches tall? You can now answer, Dan. 0.15%. You guys, is that going to happen very often? What percent are taller than 72? Now, I want you guys to notice. Is there an end point here? No. Nope. Is there an end point here?
Absolutely not.
Ideally, even though it doesn't make sense. Ideally, these go out to negative infinity and positive infinity. I have one more thing I want to add to this graph. I know you're running out of room, but so am I. We got this. If somebody is at the mean, what percent of the data is less than they are? 50%. So what percentile are they at? The 50th percentile. The mean is the 50th percentile in a normal distribution. Question? What percent of the data is less than 62? What percent of the data is less than 62?
Like 30. Like 35.
Add them. Add these up. 16. So, what percentile is someone at if they are one standard deviation below average? The 16th percentile. This is the 16th percentile. Guys, what percent of data is less than 59.5? So what percentile is that? Oh my gosh, you guys, what percentile is someone who's 57 inches tall? They're the 0.15th percentile. That's a teeny tiny percentile, but that's a thing. Okay, we're going to go the other way now. Let's see how you do. What percentile is someone who is one standard deviation above average? 84th. Time out. How did we get 84? There's 50% below here. What percent below here? All the way down. It would be 50 plus the 34. So that's 84th percentile. This is the 84th percentile. Why is that goofy?
Because it isn't.
It's not goofy.
Does a percentile like have any like?
Percentile is the percent that is less than or equal to a number. All right, you guys, tell me. What percentile is someone who is 2 standard deviations above average? 97.5th percentile. What percentile is someone who is 3 standard deviations above average?
99.85.
These are percentiles.
Are we done?
No. Okay. I have really great news for you guys.
It's always been good news.
Huh?
It's always been good news. Always have good news.
It's always going to be these numbers. Other than this one little line where our individual distributions data is. Other than that, the percentages that are between each of these here, the percentiles, these z-scores, all of that's always going to be the same, you guys. The only thing that will change is what is the mean and the standard deviation of whatever it is I'm talking about. That's all that will change. Cool? Cool. What is the standard normal distribution? Oh, no, I'm just kidding. We have to answer questions. Sorry. What percent of young women have heights less than 69.5? We actually already answered this. 97.5%. Is a young woman that has a height of 62 inches, is she unusually short?
No.
Why not?
It is within 2 standard deviations of the mean.
So, I mean, she's within, she's 1 standard deviation below average. Now, some people would say, yeah, she is because she's she's at the 16th percentile. And so, like, there's 16%. There's only 16% that is less than her. But I'm going to tell you guys, statistically speaking, 16% is kind of a lot. Statistically speaking. It doesn't sound like a lot to you, maybe, but 16% is a lot for statistics. So I would say that this would be no. She is 1 standard deviation from the mean, and 16% are shorter. Okay, now for a tough question. What proportion of young women had heights above 65?
Oh yeah, that was hard. Never mind. Right.
What do you mean you can't tell? We just labeled that graph backwards, forwards, up, and down.
Above 65. Oh, wait, we gotta figure this out now.
Well, this is some
Oh man.
Wait, it's just like.
So maybe we do need calculus. Maybe we do need to integrate. Maybe we do need to do
It's
that.
just like 49,
Okay, can you guys at least give me an estimate?
48, 46.
Is it more or less than 0.5? What proportion of young women have a height above 65?
Wait, no, why would it be 0.5? What is this?
So 65 is just to the right of the mean, right? The mean is 64.5, right? So it's like somewhere around 40 something ish, right? But what is it? You guys know what that means? To be continued.
To be continued. Okay, now do it.
We're going to come back to this in just a few moments. What is the standard normal distribution?
Unacceptable. You cannot do this.
It is the normal distribution of z-scores. You guys, we just kind of showed it a second ago. So it is a normal distribution, so it's a bell curve with a mean of 0. Mu is 0 for the standard normal distribution, and a standard deviation of 1. This is the standard normal distribution. All standard normal distributions can be transformed to sit on this particular distribution by using the z-score formula. Value minus mean divided by standard deviation. This is the normal distribution, the standard normal distribution. All distributions can be linked back to this one. It's kind of like parent functions from algebra. The parent function of a linear graph is
Oh, yeah, it's
y equals x. The parent function of a quadratic,
y equals x squared.
y equals x squared. The parent function of an absolute value,
Oh, wait.
absolute value of x. Okay, yeah. This is kind of like the parent function for all normal distributions. So, we can use our calculator to help us calculate normal distributions. All right, I want you guys to write down the steps first, and then we'll do it. Here's the steps. Second,
Oh yeah, why do we not start with first?
vars.
Why do we not start with first?
Huh?
Oh, never mind. I thought you meant like second.
Oh, no, these are the buttons on the calculator. I'm sorry. These are the buttons you're going to push. Second, vars. And then number 2 says normal CDF. Now, there is a normal PDF. You're never going to use it. Normal CDF is number 2. Here's what your calculator is going to ask you if you have an updated operating system. If you don't, I'm going to fix that for you this week. Lower, upper, mu, and sigma. So here's what your calculator wants to know. It wants to know what is the lowest number of the area you're looking for. It's the lower boundary of the area you're looking for. So this is your lowest value. Then it wants to know what is your highest value of the area that you're looking for. And then obviously you know what mu and sigma stand for, right?
It's the
the mean, and the standard deviation. Now, some of you guys, again, your operating system right now is not updated. So you are only going to see normal CDF, and it's going to have an open parenthesis. And you have to put in the lower number and then a comma. The comma is right above the 7. This will only be for this week until I update your calculator. Then you have to put in the upper number and then a comma. And then you have to put in the mean, and then a comma, and then the standard deviation. This is only if your calculator's not updated, okay? And again, that's only going to be temporary until I fix it. Okay, are you guys ready to play with this for a second? First of all, I need you guys to find the VARS button. Where's the VARS button on your calculator? It's just next to clear, right around where all of your little arrows are. By the way, if you do not have a calculator, I need you to look onto somebody's calculator. You're going to want to see this. Yeah. All right, so let's go to second VARS. Second VARS. Notice the first one says normal CDF. I'm sorry, the first one says normal PDF. We're not using that one. We're always going to go to the second option, normal CDF. Okay, now, everybody look at normal CDF. For those of you who have the updated system, meaning it asks you for these inputs. For those of you who have these inputs, what are you seeing right now where it says lower? You're seeing -1 scientific E99. -1 E99. Guys, basically what that is negative infinity for your calculator. That's a 1 with 99 zeros behind it. Okay? With no decimal. That's a pretty much negative infinity. So let me make sure you guys know how to input this. It's the negative sign, not the minus sign. The number 1. Scientific E. Scientific E is second and the comma, which is right above the 7. Second and the comma, which is right above the 7. And then 99. For those of you who do not have the update right now, you're going to want to go ahead and put that in right here. -1 scientific E 99. So -1 second comma 99. What?
Why is it -1 E99?
So it would be -1 with 99 zeros next to it. So that would be like -1,000,000, trillion. All right, one thing I need you guys to do for me real quick. Upper, I want you to put in positive infinity. How do you put in positive infinity?
1E99.
Put the number 1, put the scientific E, so that's second and the comma, and then 99. 1E99. Those of you who don't have the update, make sure you have a comma in between these two. Your mean. Those of you who are seeing this already, what is the mean that your calculator defaulted to?
0.
Standard deviation? Why do you think? That's the standard. Everybody hit enter after you put those inputs in. What do you get?
1.
Why do you get 1? You just found the percent of the curve that goes from negative infinity to positive infinity. 100%, which is 1. Isn't that cool? Now guess what? You can put in different lowers and uppers. And tomorrow we're going to go through that.